So were there any questions that you wanted to go over from the homework? Yes. 2D. Okay, so we'll start off with 2D. 2D. 2D, as in this. Oh, in the second exercise? Okay, perfect. Okay, so that one's easy. We know how to do that one. Shh, shh, shh. Guys, quiet now. All of your chit-chat is getting recorded on YouTube, so. Okay, so we'll look at, this is exercise 11B, question 2D, and we want to integrate 3 minus 2 cos half x over sine squared a half x. Now, I know some people have done this one correctly because I actually think I saw Hisham and Zubair doing this one on Tuesday's lesson. Do you remember, either of you remember how you do this question? Good, you split it into two. When you've got a single thing in the denominator, you're able to split the numerator up into two different pieces so that you should end up with, it's the same thing as integrating 3 over sine squared a half x minus 2 cos a half x over sine squared a half x dx. Then we're going to look at each of those pieces individually. What does this thing simplify to? 3 cos x squared a half x. Now this bit might need a little bit more work, but you've got a cos over sine squared. Maybe I should write that in a bit more detail. Cos over sine squared. That's the same as cos over sine times 1 over sine. So that actually is the same as minus 2 cot a half x cosec a half x dx. So what does cosec squared integrate to? Should integrate to minus cot. So it's going to be a minus, we definitely know it's going to be a minus cot a half x, and we have to also divide by the reciprocal, divide by a half, which is the same as multiplying by 2, so it becomes 6, because you're, so you get minus 6 cot a half x. This bit, what differentiates to cot cosec? Minus cosec, so this is going to be a plus cosec a half x, and 2 divided by a half is 4, and it becomes a plus 4 plus c. Now I would really strongly encourage you to check this by differentiating. So really quickly, if I was to differentiate this, I would have the minus 6 times the half, then I would also have, multiplying it by the minus cosec squared a half x. Good, the negatives will cancel, and then you've got the 6 times the half, which is the 3, so that gives you the thing that you want. If we were going to differentiate this, we would have the 4 times the half from the chain rule multiplied by negative. Cosec goes to cosec cot. You've got the 4 times the half is 2, and you've got the minus, so you've got the minus 2 in there as well. Okay? Were there any other ones from the homework that we wanted to have a look at? Yep. 3.
In the book, so I didn't know where it's from.
3J. Did I say to do 3J?
As in pass. No, I said 3J.
There's no 3J.
What? On the booklet.
Oh, he's talking about the booklet.
11B.
Oh, okay. 11B and 3J was... Oh, you want to have a look at this one?
Yeah, it wasn't in.
No, but I think I've got the answers actually I'd put up as well. I put the answers from here. And it's minus 5 over 2 ln 3 minus 2x. It's going to be an ln 1 as well. Okay? So, any other ones you wanted to go through before we move on? Okay, let's get stuck in then. We're going to be looking today at some dodgy expressions that we cannot integrate. And some of these expressions, including sine squared x, I've said actually that sine x cos x can't be integrated directly, but actually it can be integrated directly, but we also can use a trig identity for this. Let me just quickly flick this bit up here so we can see what it says. Let me move this across. There we go. So although I've said sine x cos x can't be integrated directly, we're actually going to find that it can be integrated directly in a couple of slides' time. But at the moment, we think that it can't be integrated directly. So we're going to try and do some of these expressions here, and we're going to try and use some trig identities to make it something that we could do integration with instead, okay? This is the most common one that you will be trying to integrate, sine squared and cos squared. Those are things that we will often come across trying to integrate, and we can't integrate them in a normal kind of way. We have to use a trig identity. If there's one thing that you take from today's lesson for the first half an hour, because we're going to need more of this later, it's that integrating sine squared and cos squared is not straightforward and it requires an identity, okay? Now, what are any trig identities that include sine squared or cos squared that would eliminate anything to do with the sine, the squared part in it? Cos 2x, good. The formula, I think we talked about this at the end of the last lesson, didn't we? We said that cos 2x, where should I fit this in? I might have to make this a little bit smaller for a second so I can fit some, oh, it's going to be integrating my trig identities, that's disappeared. Let's fit this in at the bottom. So we know that cos of 2x is the same as 1 minus 2 sine squared x. If we rearrange this to make sine squared the subject, what we should come up with, adding the 2 sine squared onto this side, we get 1 minus cos 2x. So sine squared x is a half minus a half cos 2x. Okay? Similarly, we know that cos 2x is also equal to what? Cos squared minus sine squared, but the one we're going to use is the one Rayhan just said, which is 2 cos squared x minus 1. So rearranging that one, we get cos 2x plus 1 equals 2 cos squared x. Halving everything, we get a half cos 2x plus a half equals cos squared x, okay? So these two things that we've got written here, I think we've actually used them previously in some kind of form. They are going to be really, really useful for what we're doing here, okay? Those identities, this cannot be integrated by itself. In the second part of today's lesson, you'll see why that's kind of true. But if you try and think, is there any expression that differentiates to sine squared x? No, because it would have to be a sine cubed x. And sine cubed x, when you differentiate it, what happens when you differentiate sine cubed x? You get 3 sine squared x. Say that louder. And you get a cos x as well. So I can't integrate this because it doesn't have a cos x with it. Because when you differentiate sine cubed, you also get a cos as well as a sine squared.
So then with the top one you can because it's double on the formula.
For which one? This one?
The sine x cos x one.
The sine x cos x we would be able to do in what we're going to learn about in the second half of the lesson, but we're going to still use an identity. So if I want to integrate sine squared x dx, that's the same as integrating using this identity that we've got down here, a half minus a half cos 2x dx. I'm going to show you something that you probably know that you can do, but these things here, they've got a common factor of a half. Do you know what you can do with that half? You can take it right to the front of the integral, just because it often makes life, it can make life easier. It doesn't always make life easier, but I just wanted to remind you that you can do that. So I'm actually integrating 1 minus cos 2x with respect to x. Now let's actually just get on with the integration. What does this integrate to? 1 integrates to? Minus a half sine 2x. Let's just double check that works. Yeah, because sine differentiates to cos, you'd have the extra 2, so you have to also divide it by 2 as well. You have to get a half sine 2x. And then at the end, you've got your plus c. So when we expand by the half, we get a half x minus a quarter sine 2x plus c. So that's what sine squared x integrates to. We could check that to see what it differentiates to. We hope that this would differentiate to this, but we're going to kind of have a look at that in a second, I think. Don't want to like dive into that just yet. Let's do this one underneath it, seeing as it's kind of in the same realm of questions that we've got there. So if I'm going to integrate cos squared x dx, I'm also going to use the same identity, not the same identity, but the same kind of family of identities that I've got. So I'm going to actually integrate instead a half cos 2x plus a half dx. I'm just going to do this one without taking the factor of the half out, just because I want you to see you can do it in either way that you like. What what is the integral of a half cos 2x? Good, a quarter sine 2x. We know that it would be sine 2x, but we also have to make sure we divide it by 2 again because of the 2x that we've got here. It's reversing that extra effect that we get from the chain rule. We then also get a half x from integrating that, and then we get the plus c. Okay? Now we're going to have a look at doing these two that we've got over here. Shall I give you a moment just to write some of these down? Yep. If you've written those, think about what the strategy would be for this question and what the strategy would be for this question. Okay, so although we're going to see in the next few slides that we could integrate this directly, this whole exercise is about using trig identities. So what trig identity does this look linked to? It looks like a sine 2x equals 2 sine x cos x. It's the double angle formula for sine 2x. So I'm going to make it the subject. So I've got a half sine 2x is sine x cos x. Things that you need to notice here, this argument can be replaced with an argument that has doubled. Okay? So, yeah, so it's going to become something, because I've got 3 x's for this argument, I'm going to replace it with a half sine 6x instead. So, integrating sine 3x cos 3x with respect to x is the same as integrating a half sine 6x. It's 6x because the angle is doubling, the argument is doubling there. And that's going to be what, Hamza? Minus a 12th cos 6x plus c. We know that cos goes to minus sign, so it's going to have to be a minus cos here to go to a positive sign. It had the half already. Why did it become the 12th? Because you're multiplying by a 6th, because of the fact that the derivative of this bit inside here would have been 6, or because of that previous thing we looked at where you divide by a, where a was the coefficient of x. Now this one I can kind of do in my head. This rearranging of the double angle formula for cosine, I personally just cannot get those yellow lines into my memory. I just can't get them into my memory. If you can get them into your memory, they're going to save you a bit of time of having to rearrange the cos 2x into those different forms. For some reason, I feel like I've reached my memory capacity for trig identities, and I just can't get any more of them in. But I would like it if you were able to try and, if you were confidently able to memorize those things, because as soon as you needed to integrate sine squared or cos squared, which is actually going to be quite a common thing, you instantly know you can replace sine squared with a half minus a half cos 2x. If someone comes up with a nice way of memorizing those, I would like to hear them, because I don't like having to always do extra work. I want to try and be as lazy as possible. So you may need to find yourself doing a bit of rearranging of the double angle formulae that we have here. Okay, last one that we will look at. I'm trying to integrate tan squared x dx. But if you recall from last lesson, tan squared is not on our standard functions that we know how to integrate. So what could I transform tan squared into using an identity? It's going to be sec squared minus 1. We know that 1 plus tan squared, if I just do that here, we know that 1 plus tan squared x is sec squared. So clearly tan squared is sec squared x minus 1. So I'm going to integrate sec squared x minus 1 with respect to x. And what is the integral of sec squared? Good, so it's tan x minus x plus c. And if you think about how this differentiates to this, because if you differentiate tan x minus x, you get sec squared minus 1, which then is the same as the identity of tan squared x. So it doesn't directly look like that differentiates that. There's definitely this identity that's kind of like bridging in between these two ideas. These ones are a lot harder to see how the result of the integration, how it differentiates to what we were asked to integrate. It's harder to see that, but it can be done with a lot of use of trig identities. You know, I'm doing my my graduate diploma. I have to use these trig identities even in like third year math stuff that you'll be doing. So it's useful to have them memorized, because they will make you speedier, better mathematicians, better engineers, better economists, whatever kind of things you're doing. All that memory is really, really helpful. Can I go on to the next page? Okay, so we're just going to do 2 more of my examples, and then you're going to practice for me on the whiteboards. We're going to try and integrate sec x plus tan x squared dx. Now this doesn't look like I can integrate this, so we better do some exploring of some things first. Yeah, so I think first of all, the instinct is definitely going to be to expand this. Now I'm going to run out of space, so I'm going to put this on a new line here. What does that expand to? Sec squared x plus 2 sec x tan x plus tan squared x. All of that is being integrated with respect to x. Please don't forget the things like dx at the end. It might seem like not very important, but it's about making sure that you're communicating in the clearest way all of the time. Now, out of these 3 different terms that I have here, which of these ones can I integrate? I can integrate, which 2 did you say, Sadia? Or Muzakir? I can integrate that, and I can integrate that. I can't integrate that. What do we do to integrate tan squared? Good. We're going to replace the tan squared with sec squared x minus 1. So can we see what the whole thing is going to simplify to then? No. There's a sec squared x and a sec squared x minus 1. So it's 2 sec squared x. Let's put in this bit then. So we've then got the 2 sec x tan x, and we've got the minus 1, and we're going to do that with respect to x. Sufyan, do you think you can do these bits of integration for me? What would be the integral of sec squared x? Or 2 sec squared x? It's just going to be 2 tan x. You were doing the third because you were doing something about the power, but remember it's just a standard 1 sec squared integrates to tan x. Hisham, what should 2 sec x tan x integrate to? 2, not sine, you know. Yeah, I think you had the right thing in your head. I think it obviously isn't going to be sine, we know that's with cos. And then we also need a, okay, good. So I guess what I'm trying to say to you here is sometimes you might look at something and be like, I don't know how you integrate that, but you just better start doing something. Expand the brackets, then say, cool, I know how to integrate that. I know how to integrate that. That's my question mark. I'm going to work on that thing and think, how do I develop that and keep moving that on as well? Maybe a trig identity will help. That's why it's so important that we know that tan squared is linked to sec squared, because we know that sec squared can integrate, blah, 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 blah. It all kind of links together. Okay, so this one that we've got over here, I'm only putting this in because I might give you a couple of questions with limits, but I know they've come out really, really badly in the printing, so we may have to, I may put those on the board. This time, if we wanted to integrate now between pi over 6 and pi over 3 as our limits, sine squared 3x with respect to x. Let's just steal from the previous slide. What did we say that sine squared could be rewritten as? A half minus a half cos, what am I going to write instead of 2x though? Good, because the angle is doubling. So whatever this angle here is, on the previous slide, we said it was a half minus a half cos 2x, so it went from x to 2x. So it's going to do the same thing here. It's going to go from 3x to 6x, and that whole thing is going to be integrated with respect to x. And that's going to go between pi over 6 and pi over 3. Because we've got limits here, this is probably where I would prefer to take the half to the front, I think. So I'm going to take the half out and go between pi over 6, pi over 3, 1 minus cos 6x dx. Don't forget the half that's still there. And then you know we use the square brackets when we actually have got limits in there. I'm going to have x, and Rayhan, what do we think this is going to integrate to? And that's all between pi over 6 and pi over 3. So it's going to be a half multiplied by pi over 3 minus a sixth of sine 6 times pi over 3 is 2 pi. And then we're going to subtract pi over 6 minus a sixth. Whoops, that doesn't really look like a minus there. Minus a sixth sine of pi, because you've got pi over 6 times 6, which is pi. Got to close off the big brackets as well. Okay, so we've still got the half outside the front. What is sine of 2 pi? What is sine of pi? 0. These things here, this thing and this thing, they are both, let's write it with words, they are both 0. So we don't even need to worry about them, which is great. So all I've got is pi over 3 minus 0 minus pi over 6. So then that's a half times pi over 6, because a third take away a sixth is a sixth. So our answer is pi over 12. Now you may not know this, but if you wanted to check the answer to this question, you can literally type this thing here onto your calculator and it will give you the answer pi over 12. Have you explored that button before in your calculator? On all calculators, you can actually do integration on your calculator. It won't give you all the marks for the question. I tell you what, if you just did that and you put the answer pi over 12 in the exam, you'd get, and it's probably an 8-mark question, you'd get 1 out of 8. Because it will say using algebra or saying not using blah, blah, blah methods. You would have to use algebra to show all of this bit here. But it's quite nice that if you get to the end of it, you can actually just type into your calculator and be like, great, the answer is pi over 12. I got pi over 12. I got full marks in that question. Move on and don't even have to think about it. And then if you don't get pi over 12 when you type it into your calculator, then you need to have a look again at your working and think, I forgot to multiply by half. It's there to give you like a bit of a clue of what you might do. Okay, so I'm going to pause us there. We're going to have a look at exercise 11C, and we've been sat down for too long, so we're going to get up from there.